good.
Yeah.
Let's go ahead. Yeah. Vision transformer. Very nice.
Okay. So yeah, hello everyone. The topic of our presentation is vision transformers, which is based on the paper and images worth 16 by 16 words, transformers for image recognition at scale. So, and this will be presented by me and Shivani. Okay. So let's move to the next slide. Okay. So the previous presentation discussed in detail the architecture of a transformer and how this self-attention based architecture has achieved state-of-art performance in machine translation tasks. So thanks to the transformer's computational efficiency and scalability, it is now possible to train models of larger sizes and parameters due to the introduction of parallelization. So, but when it comes to image classification tasks, ResNets tend to be the de facto standard in computer vision. So the question that arises is, can we apply a standard transformer directly to image classification tasks and achieve the can we achieve the state-of-art results? Okay, so with this motive in mind, the researchers at Google tried to use the transformer encoder architecture on image classification tasks, and all their findings and results have been published as part of this paper. And we would be presenting that in this paper. So let's come to the main idea of this paper. The main idea of this paper is to train vision transformers on a sufficiently large data set and then fine-tune this pre-trained model on smaller data sets. So vision transformers not only attain excellent results compared to the state-of-art CNNs by using the architecture of transformer encoder, but also require substantially fewer resources to train. So before moving into the actual architecture, let us first define our goal. So our goal is to predict the class of a given image by using vision transformer. So for example, as seen here, we pass an image to the VIT, and then the resulting softmax vectors predict the confidence score. And as we can see, as dog has the highest score, the model will predict the image class to be dog. Okay, so now let's see the figure or the architecture of vision transformer. So as you can see, the transformer encoder architecture on the right-hand side is exactly as similar or is exactly same to the one that was mentioned in the previous paper. So this is the encoder architecture. This encoder architecture from attention is all you need paper is used in vision transformers. Okay, so as you can see here, the input image is split into multiple patches which are linearly flattened. These linearly projected flattened patches are then concatenated with the positional embeddings, which are then passed through the transformer encoder block. So the positional embeddings generally keep track of the sequence of the image patches. Now the output of the transformer encoder is then passed through a multi-layer perceptron head, and the output from which we determine the final class prediction of the image. So just to make you understand the architecture a little bit better, here is an animation of the architecture. It shows how the input image is getting passed through the network. As we can see, the input is flattened, embeddings are added. It is passed through the encoder and a transformer encoder, and the output of the transformer is passed through the MLP head, which then predicts the class. So this was just a brief overview of the VIT architecture. Now every step of the VIT architecture will be explained in detail by Shivani.
Okay, so the first step in the vision transformer architecture is nothing but linear patching plus positional encoding. What it simply means is that we split the input image into some fixed size patches and we linearly flatten them out and we project them and add some positional embedding to get a final vector. To understand it a bit better, let us look at this figure over here. Suppose this is our input image. What we do is we basically divide that input image into some fixed size patches. Let the size of the patch be P. The patch size that the paper has used is 16 by 16, which states the name of the paper, that is an image is worth 16 by 16 words. And your C is nothing but the number of channels of the input image. So the patch dimension will be nothing but P by P by C. We convert this P by P by C dimension into vectors, which are linearly flattened. Hence, its dimensions become P square C by 1. This P square C dimensional 1 or this linearly flattened vector is then passed through a dense layer with randomly initialized weights and biases. And this dense layer converts this P square C dimension to a D-dimensional vector. This D dimension is nothing but the embedded dimension that is used throughout the network architecture. Once we have this D-dimensional vector, we also append some positional encodings to this vector to give a final Z vector. So let us see why these positional encodings are important. If you compare the left image and the right image, you see that the patches in both these images are exactly similar. But just by changing the sequence of the patches, the actual meaning of the original image is lost. Like the meaning of both the second image completely changes by changing the sequence of the patches. As well as the transformer has no way of implicitly storing a sequence information. Hence, to make a transformer keep track of the sequence, we explicitly add some positional encoding to the input image patches. And if we do not add that positional encoding, a 3% drop in accuracy was observed by the authors. And the positional encoding that they have used is typically 1D, that is one dimensional. Okay, so coming back to our architecture, what we do is we append a learnable class embedding or a learnable class token to the sequence of linearly flattened input patches, patch vector X. This learnable class embedding is then passed through a dense layer. And obviously, this is a most important step because the output of this class token at the last stage will determine the class information for an image. This class token was first introduced in the paper Birth. So you can go through it if you want to learn more about it in detail. Okay, so to understand all the dimensions a bit better, let us revise what we have learned so far. So suppose our input images of size 224 by 224. What we'll do is we'll convert it into patches of 16 by 16 size. Let P be the patch size, C be the number of channels of the input image. So the total patches that we can create out of this image are 196. Let us represent it by N. So after linearly flattening all those patches, we'll get a vector X, which will be N by P square C dimension, where N is the number of patches and P square C is the patch size of, is the size of each patch. We then pass this X vector through a dense layer to convert this P square C dimension to a D-dimensional vector. And this D dimension is nothing but a hyperparameter that we can set as a user, which is basically the embedded dimension that is used throughout the network. We then embed a class embedding, which is 1 by D dimensional. So the embedding vector becomes N plus 1 by D dimensional. And we also add some positional embeddings to get a final Z vector. Also, these class embeddings and positional encodings can be randomly initialized. So now once we have a vector Z, what we do is we pass that Z vector to the next step of a vision transformer architecture, which is nothing but a transformer encoder architecture. As you can see in the image, the transformer encoder architecture is exactly similar to the one that was discussed in the previous presentation in the Attention is All You Need paper. So what happens in this step is that the Z vector that we got from the previous step is passed to the transformer encoder architecture to get a context vector, which is called as C. The transformer encoder architecture consists of multiple encoder blocks. And each encoder block has a multi-head attention unit and a feed-forward unit. And each of these units are again followed by a normalization layer. We already know how a feed-forward network works. It is basically a neural network. But let us try to revise the multi-head attention concept that we have seen in the previous paper. So to understand the multi-head attention concept, let us look at this image. So as you can see, the main building block of a multi-head attention unit is nothing but the scaled dot product attention. And the scaled dot product attention is as given in this figure, wherein we need queries, keys, and values. But how do you get these queries, keys, and values? What you do is the input vector Z that you have, you basically copy it down 3 times and multiply it with some weight matrix, WQ, WK, and WV, which are also randomly initialized and learned as the network trains to get our queries, keys, and values. Then the queries is multiplied by the key vector and to get that output, which is then divided by, basically divided by the square root of the dimension. This particular step or the scaling step is basically done to prevent vanishing gradient problem in our network. Once we have this output, we apply a softmax layer as stated over here, and then we multiply it by the values vector to get a final output, which we call as a head. Now, as you can see in this image, you see that there are multiple scale dot product attention units applied parallelly. Just to understand it a bit better, let us consider H to be 8. Hence, we'll pass our input vector Z through 8 scale dot product attention units to get 8 attention head outputs. These 8 attention heads outputs will then be concatenated to form a single linear vector of d by 8 dimension. And this concatenated vector will again be passed through a linear layer or a dense network to get a d-dimensional output. Once we have this d-dimensional output, this output will be then passed to a normalization layer and again a feed-forward network and again a normalization layer. And this entire block is repeated multiple times throughout the network, throughout the transformer encoder architecture. Once the entire Z vector is passed through the transformer encoder architecture, we'll get our context vector C. Once we have our context vector, we'll come to the final stage of our architecture, wherein we are only interested in the context token C0. For classification purposes, we are just interested in this C0 context token. This context token C0 is then passed through an MLP head, and MLP is nothing but a multi-layer perceptron, which is similar to a feed-forward neural network. And so there are two different architectures of these MLP head. For the pre-training stage, we use a one hidden layer network with tanh as nonlinearity. And for the fine-tuning stage, we use a single linear layer. What do you mean by pre-training and fine-tuning will be explained further in the presentation. So with this, we come to the end of the entire architecture. Just to revise it up one last time, what we do is we take an input image, we first linearly flatten them into linear patches, and then we append a class embedding to this linear patches. We pass it through a dense layer to convert those patches to a d-dimensional Z vector. We add positional encodings. We pass that vector through a transformer encoder architecture, convert it into context vector, and then the context token C0 is further used for the final prediction. Now, the training of this network and the results obtained by the paper will be further explained to you by Anuja.
So now that we know the architecture of vision transformer, let us see what the steps of VIT model goes through, what steps the VIT model goes through. So at first, our VIT network is randomly initialized with some weights and trained on a huge data set. This is called as the pre-training step of the model. Now that we have pre-trained our model, we then try to fine-tune our pre-trained network on different smaller data sets by initializing a network with the pre-trained weights. And then finally, we apply the fine-tuned model and calculate the accuracy. So now let us see through experiments, through some experiments and results, how vision transformer have attained better results in CNNs. So the paper uses three main training data sets for the experiments, which is as mentioned in the table. So we have ImageNet dataset with 1.3 million dataset images, ImageNet 21K with 14 million, and JFT with 300 million datasets images. Okay, so now we need to pre-train our model. So the authors used three pre-training architectures, namely VIT base, VIT large, and VIT huge. The number of encoder blocks, so the number of parameters that they have used is given in this table. So the number of encoder blocks, scale dot product attention blocks, and the embedded dimension D that we were talking about before, for each of the three networks is as mentioned in the table. So all these three models are pre-trained using Adam optimizer with batch size of 4096 and the weight decay of 0.1. Now, once our pre-training is done, we move to step 2, that is we now fine-tune our model. So while fine-tuning our models on smaller data sets, the author uses stochastic gradient descent optimizer with a momentum and a batch size of 512 and 518 for large and huge models are used respectively. So further in the experiments and the graphs, you'll see the model representation to be something like VIT-L/16. So this VIT-L simply means that it is the VIT large model setup, and 16 represents the patch size. So now let us take a look into this table. And for now, let us focus on the first row of the table. So as we can see for ImageNet, the previous state-of-art model was efficient net with 88.4% of accuracy. The VIT huge model with 14 patch size outperforms this benchmark. So while the VIT large models trained on JFT and ImageNet 21K perform slightly worse than the benchmark model, but for the other benchmark datasets like Cypher, Oxford, and VTAB, the VIT large and VIT huge models performs very well than the state-of-art ResNet models while taking fewer resources to train. Now, when the author says fewer resources to train, let us focus on the last row of the table. As we can see, the number of TPU V3 core days required by VIT models are considerably less than ResNets and EfficientNet models, which proves that VIT models not only perform well, but also train much faster than the existing state-of-art models. Okay. So now in the next slide, we'll see some more figures. Okay. So here in the first image, we compare various VIT architectures with the ResNet for different pre-training data sets. And as observed here, VIT model variants trained on larger data sets are performing better than the BIT model. The BIT model here is represented by the gray dot, and the rest are the VIT variants. So a BIT is nothing but is a ResNet model, by the way. And the highest accuracy, as we can see, is obtained by VIT huge model with 14 path size when pre-trained on JFT 300 million images. That is the huge data set. Now in the image 2, here we train our models on random subsets of JFT data set. And as we can see, ResNets perform better with smaller pre-training data sets, but plateaus as sooner than the VIT architectures. And VITs perform better when with larger pre-training data sets, when larger pre-training data sets are used, and that can be seen here. So to conclude all our findings, it is safe to say that vision transformers trained on ImageNet dataset with 1 million images perform slightly worse than the state-of-art ResNet models, whereas ImageNet with 14 million dataset achieves comparable performance to the ResNets. And vision transformers, when trained on huge datasets like the GFT 300 million images, performs better than the ResNet models. So thus we can say that the simple yet scalable strategy of VIT, when combined or coupled with pre-training on large datasets, matches or exceeds the state-of-art performances of many many image classification datasets, and these are relatively cheaper to pre-train as well. Thus, the paper explored the direct application of transformers on image recognition. But while these initial results are encouraging, the paper sets future scope to analyze performance of VIT on computer vision tasks such as detection and segmentation. By stating the scope here, we end our presentation, and we are open to any other questions.
Questions?
I noticed there was I think one of the images was just like the one from the previous presentation. Is that like a common image to describe the transformers? I don't know exactly which one. It was in the beginning of the slide.